Hi, welcome to our session on similarity. We're going to start off with a very basic question which says, prove that triangle GLH is similar to triangle GKI. You'll notice that I've highlighted the small triangle in red, and we want to prove that similar to the big triangle. Now, on inspection, you would agree with me that angle G is common. We can also conclude that angle L is equal to angle K due to corresponding angles. And then our last one or conclusion would be that angle H is equal to angle I because both these triangles add up to 180. So we can use something called sum angles of a triangle. I know some of you may be thinking also corresponding angles. But in similarity, all we have to do is prove two angles equal, and the third angle will be equal due to some angles of a triangle. So here I have my skeleton, and if you look at my skeleton, it says in triangle GLH and GKI. Order is very important. And then we're going to conclude, therefore, they are similar, and our case would be angle, angle, angle. So we're going to write down what we put down in the diagram, which is number 1. We said that angle G is common. Number 2, we concluded that angle L is equal to angle K. Remember to put a copy sign on L and K. And our reason there is equal corresponding angles because LH is parallel to KI. And number 3, we can conclude that angle H is equal to angle I, and that is some angles of a triangle. And therefore, these two triangles are similar. Case, angle, angle, angle. Now, whenever we prove two triangles similar, we can then conclude that the ratios are in proportion. So if we're looking at the ratios, if we take the first two on our left, we could say that GL over the first two on our right, so we can conclude GL over GK is actually equal to, and now we're going to change that to the last two, which is equal to LH over the last two on my right, KI. And we're going to take the first and last, which is GH over GI. So here we have our ratios. And what is very interesting here is to see that from ratio and proportion, we would have concluded that GL over GK is equal to GH over GI. But from similarity, we can now form a relationship and conclude that GL over GK will be equal to LH over KI. So that comes out from similarity, which is very important when we're proving later on if we have a common angle and these two sides are parallel, and then the conclusion would be that the small triangle would always be similar to the big triangle, and we don't have to prove that later on. And then we can conclude that this third side we normally talk about in the triangle, LH over KI, is actually equal to GL over the entire side called GK. And our reason for these ratios is from the above similar triangles. So let's start with some past paper questions. So read our first question, and in this question it says, in the diagram, triangle PQR is a right angle triangle. It's marked for us, which means 90 degrees. They also tell us that ST is perpendicular. ST is perpendicular to, or ST is a perpendicular bisector. So we break the two words down. It's perpendicular, that means T1 would be 90. It's a bisector, means that it bisects the side PR. So let's go a little deeper into that. And it now wants us to prove that triangle PQR is similar to PTS. So I've highlighted the big triangle PQR, and now I'm going to highlight the small triangle PTS. Now remember what they told us on the top. Okay, they told us that ST is a perpendicular bisector. So remember we have T1, which will be equal to T2. We'll look at that a little later. So if we look at this, both the triangles, number one, we can conclude that angle P is common. Okay, and then remember what we said, it was a perpendicular bisector, which I'm going to mark now. T1 is 90 from the statement, T2 is 90, and also PT is equal to TR as the side is being bisected. So let's put it together now. We're saying number one, in triangles PQR and PTS, angle P is common. Number two, we have angle Q is equal to T1. And the reason is because ST was perpendicular to PR. Remember, Q was given to be 90. And number three is angle R, which is our third angle in the green triangle, will be equal to angle S1, and that is your sum angles of a triangle. And therefore, we can conclude that these two triangles are similar. Case AAA, angle, angle, angle. Moving on from that previous question, it now gives us lengths. It tells us that PR is 16 and QR is 14. So we have QR is 14. If PR is 16, we know that PT would be equal to 8 and TR will be equal to 8. So they want us to find PS. So what we're going to do is put our sides in. That was given to be 14. And because PR is 16, we're going to use 8, 8. Now remember in the previous question, we proved that triangle PQR, which was the big triangle, was similar to PTS. So let's derive the ratios from here. From here, we can conclude that PQ, that's the first two, over PT is equal to QR over TS, which is equal to my PowerPoint just... Okay, sorry for that. I just jumped a slide. So remember what we are saying now. From this, we have the first two is PQ over the first two is PT is equal to QR, that's the last two, over TS, which is equal to PR first and last, and that should give you PS first and last. Now, we don't have to use all. So remember, our question is to find PS. So if we look at the bigger picture on this, so we know PR over PS. So if you look at PR, do we know what's PR? And the question is yes, we can replace PR with 16. And then if we look at QR over TS, do we know what's QR? Yes, 14. And do we know what's TS? TS we don't know at this stage. Then we can go to PQ. Do we know what's PQ? Not at this stage. And do we know what's PT? Yes. So you'll notice that we can find, if I look at this ratio, I can find PQ using Pythagoras, which we're going to do. So PQ is equal to, we can write down Pythagoras, that PQ squared is actually equal to 16 squared, that's your hypotenuse, minus 14 squared, which actually gives you PQ to be equal to the square root, and I've indicated that down for you here, which is equal to 2 root 15. So we know PQ is equal to 2 root 15. So therefore now, just want to use my eraser to erase all this out. And therefore we now know that PQ over QT, which is equal to PR over PS, we have the main sides. Okay. And I'm going to erase that as well so you can see it clearly. So we're going to replace the values. Now we just found PQ to be 2 root 15. PQ we found to be 2 root 15. PT on the diagram is 8. And then we have PR, which was 16. And then we're trying to find PS. And then we can cross multiply, which we want to do now. And we could say from here, PS is equal to 16 times 8, and then we're going to divide that by 2, which you can find using your calculator. And that was a very simple question to work with. So we're going to move on to another question, maybe a little bit more trickier this time, integrating circle geometry. And this question says, in the figure, AB is a tangent. As soon as you hear this word tangent, you got to think about tan chord theorem. And if I quickly just inspect that, we could conclude that A4 is equal to D1, which is your tan chord theorem. Could also conclude that A1 is equal to D2, tan chord theorem. And it goes on to tell us circle center O. Remember, if we have a circle center O, it makes AO equal to OD radii. So I'm just pointing out some things as we move along. AC is equal to AO. I guess that's given. But what's quite interesting is that AO is actually a radii, which will mean that it's also equal to OD. Might help us later on. BA is parallel to CA. BA is parallel to CE. So when I look at parallel lines, immediately I'm looking for, I'll see an alternate, A4 and C2. That could help us later on. We also see alternate A1 and E2, which we'll use a little later maybe. And it goes on to say that DC produced cuts the tangent at BA, cuts tangent BA at B. Okay, so let's get into the first question here, which says, show that C2 is equal to D1. So let's quickly go and look at, there's D1, and we're trying to prove it equal to C2. So we're going to get D1 and C2 to be the same. So normally what I like to do is start with one of the angles being X. Doesn't matter which one. Call C2X or D1X. So in this case, I'm going to call D1X. So if I call D1X, and I'm going to write that down. So we're going to start off by making a very bold statement in saying that let angle D1 equal to X. So if we look at the diagram, if D1 is equal to X, we can now conclude that A4 is equal to X. And the reason why A4 is equal to X, that would be, and I'm not going to write the reason down so you can jot it down. That's your tan chord theorem, angle between the tangent and the chord. Notice there's the chord, if you can't see it. Here's it, angle between tangent and chord is equal to D1. And then from there, we could go on to say that C2 is equal to X. And why is C2 equal to X? Well, that's a simple alternate angles, equal alternate angles. And we actually started off by saying D1 is X, and we concluded by saying that C2 is X. And then we can make a conclusion, therefore, D1 has to be equal to C2. okay, because both have been proven to be x. So we're moving on to the next question, and that wants us to prove that triangle ACF is similar to triangle ADC. So let's start off by highlighting those triangles. There's our first triangle ACF, and we want to prove it's similar to the green triangle, which is called ADC. So by inspection, immediately when I look at those two triangles, I see a common angle. And that common angle I'm looking for is A3. So you'll notice that A3 is actually common to both the triangles. The second one we look at is angle C2 is equal to D1. I want to remind you that both are x, C2, which we proved in the previous question. So we've already got two angles. The third one, or the third remaining angle, would be equal due to some angles of a triangle. So what we want to do is quickly just point it out. In the big triangle, we used A3. We used C1. So we haven't used the entire of angle C. And in the small triangle, we haven't used F1. So that will be our last concluding statement, that F1 is equal to ACD, or C1 and 2, and that is some angles of a triangle. And therefore, these two triangles become similar, and the case is angle, angle, angle. Going on now to the last question here, which said that prove that AD is equal to 4AF. So we're working with sides, and what's going to help us here is the corresponding sides, the corresponding ratios being equal. So if we look at in the previous question, we proved that ACF was similar to triangle ADC. Okay, that's what we proved in the previous question. So we're going to use that fact. And also remember, it was given initially that AO is equal to AC. And then I did mention to you, due to radii, it means that this will also be, AO is also equal to DO due to radii. So from the above, if we look at AD over AC, I took the first two here, AD over the first two here, AC, and I'm starting with AD because that's the question. AD over AC would be equal to, and I'm taking the last two, which is AC over AF. And the reason why I'm using that is because I know I can make a conclusion with some of these sides. So we started with AD because that was a question, over AC. You'll notice I'm using AC, okay? Because AC is equal to AO. So in other words, if we were using a letter here, just to make you understand this, that if that was a letter called for a side, let's call it K units, then this means that that will be K units and that will be K units. And if you actually put that together, we're basically saying from here, AD, which we know is now 2K units, over AC, and AC is K units, will actually be equal to, on the right hand side we got AC, which is K units, over AF. And we don't know at this stage what AF is. Okay, so that's what we kind of trying to put together. Now, putting into ratio and proportion, okay, we are saying AD over AC, but remember AC is actually equal to half AD, which is equal to, so I'm replacing all the ACs with half of AD. Okay, so a very important statement I'm trying to make here, if you're not catching that one, is that AC is actually equal to half AD. So if we do it this way, the ADs and the ADs will cancel off. And if we cross, actually not if we cross multiply, but we would get 1 over half is basically 2 over 1. Okay, let me go back there and just make a point. I'm going to erase that. Okay. So from a understanding point of view, we can see that that and that will cancel off, and half times half is 1/4 AD. So if we cross multiply, we would get 1/4 AD is equal to AF. And multiply both sides by 4, we would get AD is equal to 4AF, which actually proves the question. Coming back, if we couldn't see it that way, we could use the K method and bring in K units. And from here, you could cancel off these Ks, okay? And you'll end up with, by cross multiplication, that K is actually equal to 2AF, okay? But remember, we want to bring it in relation to AD. And in terms of AD, we have AD. So remember, I'm saying that K is equal to 2AF, which now solves for AF to be equal to half K. And then you could substitute that in and it would work out for you. Okay. In other words, we could put all the K's back into the equation and then come out with the same answer. So that's another way to look at it. Okay, we're going to take another question, or last question on similarity. And it says, reading the question, which we're going to start off with, in the figure, PQ is the diameter. So if PQ is the diameter, immediately the theorem that I'm thinking of is angle in the semicircle, which is R1 should be 90. SP is a tangent. If SP is a tangent, I'm thinking tan chord theorem. That would give me P2 would be equal to the entire of Q. So I'm just trying to point out certain things before we go on. So the first question here is, why is PRQ? Why is PRQ equal to 90? And the reason was, in the previous opening statement, they told us that PQ was a diameter. So we're using the theorem that states angle in the semicircle, there's our diameter, angle in the semicircle is 90 degrees. Next question there is to prove that P1 is equal to S. P1 is equal to S. Okay, so I'm going to call P1 to be X. As you can see, I have angle P1. In other words, that's my let statement. And then from there, we can conclude, okay, we know the entire of angle P is 90, and that is due to the radius or the diameter being perpendicular to the tangent. Okay. But very important for us to pick up now is that angle Q is actually equal to 90 minus X. And that is because some angles of a triangle, if you actually look at the triangle PRQ, these three angles have to add up to 180. We have R is 90, X, therefore Q is equal to 90 minus X, and we're going to say some angles of a triangle. Now, from there, we can also look at the big triangle, and that's quite interesting to look at. Let me write that down first. If we look at the big triangle, and we want to find angle S, and what big triangle am I talking about? Let me highlight that for you. Okay. We look at that big triangle and use some angles of a triangle. You'll notice that the entire angle here is 90 degrees, and that's 90 minus X. So using some angles of a triangle, that angle will turn out to be X. So we can conclude that angle S is equal to X, and once again, that'll be some angles of a triangle. And that concludes for us that P1, and we can conclude now that P1 is actually equal to X. Okay, which is actually equal to angle S. And that was the initial question. Next question. Yeah, looking at the next question. Okay, I just want to erase this first. Okay, look at the next question here is we want to prove 12.4 to 12.3. So we finished 12.2. We're going to prove that SRWT is a cyclic quad. You'll notice I've highlighted that for you in blue. What we can do there is, let me just erase the yellow so you can see it a little clearly. And what I've done there was, if you look at the blue, P1 is equal to X. And we are trying to prove that SR, I'm going to highlight those 4 points, WT is a cyclic quad. But if you look at my blue highlight, I'm looking at, if you didn't see it as yet, angles in the same segment. You'll notice that P1 is equal to W because of, get that right, sorry. So we got W is equal to P1. If we look at from chord RQ, we have angles in the same segment. Now, if that is true, and I want to write that down for you, so my statement there is to say that angle W is equal to angle P1, all right, and that is angles in the same segment. But you'll notice that angle S has been proven to be equal to X. So therefore, we can conclude that angle S is equal to angle W, okay, because S was proven previously. And you'll notice now that angle W2, which has been proven to be X, is equal to S. That's what we're trying to do there, okay? You could call it W2 and make sure you have a 2 here because I can't see the 2 there. And that is the converse of exterior angle of a triangle. So therefore, we can actually conclude that SRWT is a cyclic quad. And what are we using here is the converse of exterior angle of a cyclic quad. Okay, and that proves question 12.3. We're now going to go on to similarity. And the first question there on similarity is to prove that triangle QWR is similar to QST. QWR and QST. So the first thing I want to do there is highlight those two triangles. So that's your green triangle, which is QST. Let's put it in. And then we're trying to highlight the small triangle, which is QWR. Now, on inspection, immediately you would see that angle Q1 is common. So let's write that down. So we are saying, number one, I'm not going to write the skeleton. I'm sure by now you caught the skeleton. Number one, we got that angle Q is common in both those triangles. And if you're looking at number two, we've already proven that angle W in the blue triangle, and I think we call it W2, so just make sure we're calling it W2, will be equal to angle S, which we proved in the previous question, so you can say proved above. And number three is our last angle in the blue triangle is angle WRQ, which will be actually equal to the last angle there would be T2, and that would be sum angles of a triangle. And therefore, we could conclude that triangle QWR is similar to triangle QST. Make sure you have your triangle sign. And our case here would be angle, angle, angle. Make sure you write down your reasons. Remember, W2 was equal to S2, proved above, and the last one is sum angles of a triangle. So that completes question 12.4. I'm going to erase that. So we have space for the next question, which seems to be dealing with ratios and looking at the corresponding sides. So the question there is, we want to prove, they gave us QW to be 5, TW to be 3, QR to be 4, and WR to be 2. And they want us to find the length of TS. So before we do that, or go to the ratios, let's just take a step back to put the information in. QW is 5, QW is 5, let's put that in. TW is 3, QW, so we have a 3 sitting in there, which means that the total length of that is 8. Okay. Then they tell us QR is 4 and WR is 2. Okay. So we want to find TS. So remember, I opened with this, we have proven that triangle QWR is similar to triangle QST. Now, if we want to find TS, let's look at where TS is. TS is sitting right there. So we could say TS, so I'm taking the last two, and we will have to take it over RW. Now let's look at our diagram. We know RW is 2, which will be equal to, and I'm going to use QT. If I use QT, I'll have to use QR. So we would take it QT, that's the last two, over QR. And now let's just replace what we know. RW is 4, QT we know to be 8, and QR is 4. So we can now say and cross multiply and say 4TS is equal to 32, dividing both sides by 4. We would get TS, and I'm getting 8 on that one. So putting it back on my PowerPoint, sorry, we got TS to be 4, so I have made a mistake somewhere. And I just want to go back to look at where the mistake is. Let's get back there, which I'm going to erase. Okay, let's say if we go back a statement here, and the mistake is we said RW is 4, and that is a mistake, so that we had to say is actually, according to the diagram, is 2. Now if we cross multiply, we will get 4TS is equal to 8 by 2 is 16, and that gives us TS is equal to 4. So there's our 4 coming in there, and that makes perfect sense in what we're trying to accomplish here. Okay, so we got our TS to be 4. The last question is to find SR. And if we look at the diagram, SR, so it's that part. And we can use ratios and proportion again. I just want to clear my slide. And using ratio and proportion again, we'll come up with SQ. If we look at SQ from the ratios that was previously given, that SQ is the whole side over QW. And then we have QT over QR, and that comes straight from the ratios. Now, if you can't see it, I just want to go back. SQ over QW, and from the top, SQ over QW is equal to QT over QR. And remember, we have most of the sides. So we're trying to find SQ, and the reason we're trying to find SQ, because if we can find SQ, then SR, we will take away the 4. And we know QW in the diagram is 5, given. We know that QT from the diagram, QT is 8, and from the diagram QR, if we look at QR, and that was given to be 4. And if we cross multiply, you get 4 SQs equal to 8 fives, which is 40, and we divide, we'll get SQ to be 10. And if SQ is 10, we can now conclude that SR is 10 take away the 4, giving you 6. Thank you.